Okay, welcome back, and today we're going to talk about confidence intervals again. And so this time we're going to deal with confidence intervals involving two samples, two populations. Okay, so now it's going to be very similar to what we did with one population, and since we've already gone through two population hypothesis testing, you've already seen some of the standard errors and things that we're going to use. Okay. So I'm going to go over the formulas for the confidence intervals in all three cases. Two means, difference of means, right? When we know the sigmas and we don't know sigmas. And then we're also going to look at the difference of proportions for a confidence interval. Now, keep in mind that you just need to remember the pieces that go into the confidence interval. The point estimate and the margin of error, okay? And so we've seen the pieces that go into the margin of error for the most part. And then we know what the point estimate is going to be because we've seen that in the confidence intervals. So it's not going to be brand new because we've seen confidence intervals in earlier chapters for one population or one sample, okay? So why would we want to use a confidence interval? Well, sometimes we want to have an idea of how different the two means are, or how different is the true difference of the proportions, right? And so just like we used confidence intervals in one population or one sample, there are lots of situations where we want to know, hey, what is the true difference? What is the range of those values? So that's what we're going to talk about, okay? So here are the formula. Remember, the anatomy of a confidence interval. So anatomy of a confidence interval. Okay? So what do we got? We have the point estimate and the margin of error. So we have our point estimate plus or minus our margin of error. Well, let's look at, I'm going to do this step by step, so we're going to look at the difference of means. So in this case here, we want a confidence interval for the true difference between population means. So in other words, we want the confidence interval for mu1 minus mu2, right? Now, what is the point estimate that we're going to use for mu1 minus mu2? Well, think about it. What was the best point estimate for mu? It's the sample mean. Well, if the best point estimate for mu1 is x bar 1, the sample mean from population 1, and the best estimate for mu2 would be x bar 2 from a random sample from population 2, then doesn't it make sense that the best point estimate would be x bar 1 minus x bar 2? Yes. So our point estimate is going to be x bar 1 minus x bar 2. And then now our margin of error. Remember the margin of error calculation for one sample? Well, we had our z alpha divided by 2, right, times the standard deviation of x bar. Well, guess what we're going to use? We're not going to use the standard deviation of x bar. We're going to use the standard deviation of x bar 1 minus x bar 2. And that's what we learned when we were dealing with hypothesis testing. So now, again, we're going to assume, right, for the time being, we're going to assume that sigma is known. Okay? So that means we're going to be dealing with a normal distribution. Okay? So again, remember the assumptions. Either both populations are normal or the sample sizes for both samples have to be greater than or equal to 30. Okay? If that's the case, then we know the sampling distribution has of x bar 1 minus x bar 2 is normal. Remember that's again is from earlier talks on hypothesis testing. So now it's going to be alpha divided by 2, so z alpha divided by 2 times the standard deviation, which is, if you remember, sigma 1 squared over n1 plus sigma 2 squared over n2, and then you take the square root of the sum. And so this is the formula for a confidence interval for the difference of means when sigma is known. Okay, now, on the calculator, this is what you're going to use on the calculator to give you the interval. It's going to be 2 samp z int. So it's going to be 2 sample z interval. Okay, so that's what we're going to use. Okay, so now, what if sigma is not known? Well, just like in Chapter 8, if sigma is not known, then what do? We replace z with t, and we replace sigma 1 and sigma 2 with S1 and S2. And that's it. Now, here's the thing. Hold on, let me just double check. Yep, that's it. So now, here's the thing, is that they look complicated, but they're using the same theme from Chapter 8, okay? Here's the standard error, here's the point estimate, and here's your critical value, okay? So again, now if we don't know sigma, then instead of using the 2 samp z int, we're going to use 2 sample t int. And that's it. So now, let's see if we can do an example. So now, let's see. We can put this to work for us. So now it says, a field researcher is gathering data on the trunk diameters of mature pine and spruce trees in a certain area. The following are the results of his random sampling. So they give us the sample mean for both pine trees and spruce trees, the sample size for of pine trees and spruce trees, and the population variance for each one too. So now, so they give us the population variances for these. So we're going to use a 2 sample z-test, or z interval, right? So this says use the data to find a 90% confidence interval for the difference in mean trunk diameter for pine and spruce trees, and then interpret the interval. So again, it's very important to be able to interpret the interval. Okay, so we're going to do that as well, and I think you'll understand. And it'll make complete sense to you guys when you see this example, because it's going to harken back to the same thing that we did in Chapter 8. So let me do this. Let me take a drink. So now, we want a 90% confidence interval for what? The true difference between the average trunk diameter of spruce trees and pine trees. So mu1 minus mu2. And again, which population are you going to make? So let's make pine is population 1, spruce is population 2. Okay, so now we know how we're going to subtract. So now we're going to take our point estimate, so it's going to be x bar 1 minus x bar 2 plus or minus. Now, here's where, again, you should know these things by now or be able to get them easily. 90% confidence interval will give you what confidence or what critical value. You should realize that it's going to give you what? It's going to be a 1.645, okay, as your z alpha divided by 2, okay? And then this is going to be the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay. So now, again, this 90% should give you z-score by either you just know it or you can use inverse norm, right? And either way, it'll give you 1.645. So now, based on the data, again, I'm going to tell you what the data is, but based on the data and my critical value, I just plug and chug. That's it. That's all you guys are going to do. So let me plug and chug. And so it's going to be, again, pine is 1 and 2. So it's going to be, here's the data. So here's pine and spruce. Okay. So we've got x bar 1 is equal to 35 centimeters. X bar 2 is equal to 30 centimeters. Sample size N1 is equal to 40. N2 is equal to 80. And now the population variance, sigma 1, is equal to 160. So this is population variance. Be careful. It's not standard deviation. It's variance. And then sigma 2 squared is equal to 160 as well. Notice that the variances are equal. Hence, right? But we know what they are, so it doesn't matter. Okay. In this case, remember, equal variances isn't going to matter because we know them. So don't worry about that. So now let's plug and chug. Okay, so what do we get, right? So we're going to get what? 35 minus 30 plus or minus z alpha over 2, right? That's going to be 1.645 times the square root of what? 160 over what? 40 plus 160 over what? 80. And so now I'm just going to plug and chug and get my margin of error. So what do we get for the margin of error here? Let's calculate it. Okay, so now we get $160 divided by 40. Okay, I get 4.029. So 4.029 is my margin of error, and this is 5, right? So 35 minus, so that's 5. So now what do I get? Okay, so now, again, I'm going to erase this so I can have more room. So you guys should have this written down. So now, what do I get? I get 5 plus or minus 4.029. So what do I get for my confidence interval? I get what? I get 0.971. And then I also get 9.029. So here's my confidence interval, guys. So I am 90% confident that the true difference between the average diameter of pine trees and spruce trees is somewhere between this number, 0.971 centimeters, and 9.029 centimeters. So let's understand what this means. These represent the differences, okay? The average differences between the diameters of pine trees and spruce trees. Now it's positive, which means, what do we notice about spruce trees? Well, pine trees were first, so you're taking pine tree diameters minus spruce tree diameters, and we have positive values. Notice also 0 is not in the interval. So if 0 is in the interval, then we would be able to conclude that there really is no difference. So here, it looks like the true difference between the average diameter of pine trees and spruce trees is somewhere between 0.971 centimeters and 9.029 centimeters in favor of pine. So it seems like pine is, has more girth. Okay, larger diameter. Okay, that's it. That's it, guys. So let's do one more. Oh, by the way, let me do. Okay, so let me use the calculator. I forgot to use the calculator. So let me use the calculator. So again, here with the calculator, we would use again 2 samp z int. Okay. Now, let me show you what you put in there. So let me go to stat tests. We'll scroll down to all the way to 2 samp z int. And now we're using statistics because that's what the data they gave. They gave us statistics. So we use statistics. Now it's going to ask us for all this information. So sigma 1 is 100. Oh, 100. Ooh, it's asking me for sigma. So what did the problem give me? It gave me variance, population variance, right? So I need to take the square root of this, okay? So I need to take the square root of 160, which is great. I can put it right into the calculator. I don't have to do it separately. So I'm going to just type in, for sigma 1, I'm going to type in the square root of 160. And then I'm going to hit enter. And now I'm going to do the same thing for sigma 2. So I'm going to hit the square root of 160. And now what's x bar 1? X bar 1 is 35. N1 is 40. X bar 2 is 30. And N2 was 80. Notice how the sample sizes are both at least 30, which is great, okay? Because they did not tell us that the populations were normally distributed, but they give us a sample size of 40 and 80, which is both at least 30, so we're good. So just remember that. Confidence level is 0.9. And now calculate. And look at that. We get the same thing, 0.971 and 9.029. We get the same thing. Same answers, guys, using the calculator. So let's do, let's see. Let's see here. Okay. I'm going to show you this one. I'm not going to do it because the data is big, but I'm going to show it to you because I want you guys to do it. This would be good practice for you guys. I'm not going to take the time to write this all on the board and enter in the calculator, but here this is something I could put on the exam. So it would behoove you to try this out. So it says a professor at a large community college wanted to compare the mean final exam scores between students who took his statistics course online and the students who took his face-to-face statistics class. The randomly selected 30 final exam scores from each group are listed below. So now, here are the numbers. And this is also on page 418 of the textbook. Okay? So here are the numbers. Okay, so I'm going to write like that. Okay, so if you want to pause it and write these numbers down, go for it. Okay, so now it says calculate a 95% confidence interval for the difference in means and interpret the interval. So now in this case here, they don't give us the population standard deviations. Okay, or yeah, so that means we're going to have to, all they give us is the data, so we're going to have to use a 2-sample t interval on this one because we don't know sigma 1 or sigma 2. So let's set this up, okay? So we're doing a 95% confidence interval, right? They want a 95% confidence interval for what? mu1 minus mu2, right? Because they're talking about mean scores. They want the differences in mean scores. So there's your key phrase, differences in mean scores. mu1 minus mu2. And so now, since all they give us is data, well, I would put L1, you know, the online class data, right? Scores. And then L2 would be the face-to-face scores, right? So you'd enter your data into L1 and L2, and then what you would do is you would go to your 2-sample t interval, and in this case you would check data. Right? So you use the data input option, and so after you put the data into your list 1 and list 2, go to 2samp tint, hit data, and then all you're going to do is fill in the information. You're going to tell where your list 1 is, right? So you're going to have your 2 lists, list 1 and list 2. So it'll be L1 and L2. And then it's going to ask you for your C level, right, your confidence level, which is 0.95. Now, again, it's going to ask you, just like with confidence intervals, are you going to pool the data or not? Okay. Now, since it doesn't tell us anything about the population standard deviations, we don't have any reason to believe that they're the same. So we're not going to pool in this case. So we're going to select no. And so once you do that, then what you're going to do is you're going to get a confidence interval that is negative 19.67 to negative 4.59. Now, here's the thing. Let me find out how they did the populations. They said let mu1 be the mean for online classes. Okay? So they said let mu1 be the true mean for the online classes. Let mu2 be the true mean for the face-to-face classes. So this is population 1, this is population 2. So now if we subtract mu1 minus mu2 and we get this, now we know what the negatives stand for, right? The differences are negative, right? And so 0 is not in here either because it doesn't go from negative to positive. So 0 is not in here. So there is a significant difference, it seems like. So what does this mean? Well, the true difference in the average scores between students in the online class and the face-to-face class is somewhere between 19.67 points and negative 4.59 points. In favor of what class? Well, if we're subtracting this from this and it's negative, that means the face-to-face class has the higher scores on average, okay? Because it's negative. So that means this is bigger than this. So the face-to-face class tends to have a higher average than the online class. Well, what's the difference? Well, that difference could be anywhere from 19.67 points in favor of face-to-face class to 4.59 points in favor of the face-to-face class. So this is basically how much better you could do in the face-to-face class on average. Anywhere from this many points to this many points. Okay, I hope that makes sense. Okay, so let's do one more dealing with proportions and we'll wrap it up. So now, with proportions, this is the confidence interval formula that you would use. So again, if we're looking for a confidence interval for the difference of proportions, so P1 is, population 1, right? I don't need to write that. So it's going to be P1 minus P2, right? The true difference between the population proportions. And of course, so what are we going to have? Well, we're going to have our point estimate, and that's going to be P hat 1 minus P hat 2. And just like we saw with hypothesis testing, as long as those conditions are met, all 6 of those conditions, then we know the sampling distribution of P1 hat minus P2 hat is normal. Okay? So this is going to be, this is the point estimate, plus or minus the margin of error, which is going to be Z alpha divided by 2 times, and of course, this shouldn't be a surprise, it'll be P1 hat times Q1 hat over N1 plus P2 hat times Q2 hat over N2. And so this is the margin of error. So that's going to be the calculation we do for calculating the confidence interval for the difference, the true difference between population proportions. And now the function on your calculator that will also give this to you is 2 prop Z int. 2 proportion Z interval. Okay? And so that's what we're going to use. So now, let's do an example. Researchers for a cell phone company conducted a study of smartphone use among adults. They wished to compare the proportion of smartphone users among 2 different populations: adult whites, non-Hispanic, and African American adults. The results of the survey indicate that of the 232 African American cell phone users randomly sampled, 5% have an iPhone. Of the 1,343 white cell phone owners randomly sampled, 10% own an iPhone. Use this data to construct a 95% confidence interval for the difference in population proportions. Okay, so let's set this up. So the first thing is we need to decide which is going to be population 1, which is going to be population 2. So let P1 equal the proportion, the true proportion of whites who own an iPhone. And let P2 be the true proportion of blacks who own an iPhone. Okay? And so now what they want is a 95% confidence interval. Is it 95? Let me check. Yes. They want a 95% confidence interval for what? The true difference between these. So P1 minus P2. Okay? So again, we're going to use the formula P hat 1 minus P hat 2 plus or minus our margin of error, which is Z alpha divided by 2 times the square root of P hat 1, Q hat 1, or excuse me, 1 over N1 plus P2 hat, Q2 hat over N2. Okay, now, if we plug and chug, then what are we going to do? So here's the information. Okay, let's find this out. So now it says that 232 African American cell phone users, owners randomly sampled, 5% have an iPhone. So we have to say what's 5% of 232? Okay, it's going to be so 10% is 23.2, so it's going to be 11.6. Okay, so 11.6, so we'll just say 12 because we're going to round, right? We have to round. So the first thing is let me come over here and let's write down the information. So here's let's write down the information. So we need to know P hat, which P hat is equal to N1 times, what is it? Oh, N1 times, or excuse me, I'm sorry. P hat is equal to X1 over N1. So that's going to be P hat 1. And then Q1 is going to be equal to 1 minus P hat 1. And so if we look at that, we just plug in the numbers, and the answer is going to be what? It's going to be, let's see, of this group, it's going to be 1,343. So it's going to be 10%. So in this case here, oh, let me hold on a second. So of the whites, we have N1 is equal to 1,343. And we know that 10% of those own a cell phone. So X1 is going to be 0.1 times the 1,343. So what does X1 equal in this case? Oh, is it 10%? Hold on. Yes. So in this case, it's going to be what? 134.3. And so what we're going to do is we're just going to round that to 134. So that's going to be X1. Okay. So now we get X1 and N1. Okay. And here we got N2 is 250, what was it? 232. Okay. And so x2 is going to be what? 5% of this. So it's going to be 0.05 times 232. So x2 is going to equal 11.6. Okay, so now this, and again, we're going to use 12. We're going to round up to 12. So in other words, what we have is this. Should have made this a little lighter. So N1 is going to be 1343. X1 turns out to be 134. Okay, and we know P hat, in this case, P hat 1 is what? P hat 1 is 10%. Okay, 0.1. Over here, N2 equals 232, and we calculated that X2 is equal to 12. And we know that P hat, based on what we just was given, is 5% or 0.05. Okay, and the confidence level equals 0.95. So now, with that being said, now we can plug this into the formula. Okay, now we have everything we can plug in the formula. So this is going to be, what is it? Well, it's going to be 0.1 minus 0.05. So that's going to be this piece, 0.10 minus 0.05, plus or minus. Now, 95% confidence interval, we should know that that's going to be a 1.96 critical value. Okay? And now, if we plug in the other information here, all we have to do is plug in our P hat and Q hat. Okay? So if P1 hat is 0.1, then Q1 hat is 0.9. So all we're going to do is stick in the data. So it's going to be 0.1 times 0.9 divided by 1343 plus, then we're going to take this here, and it's going to be 0.05 times, yes?